going to discuss about the interpolation with equal and unequal intervals. Actually, it is the second unit in numerical methods for final year students. First of all, what is meant by equal and unequal intervals? In a real line, when we take any 2 points, for example, some x0, x1, x2, the difference between that means the interval between the x0 and x1 and x1 and x2 should be equal. Here, for example, we take the general notation some small h. If the difference is the same, then we call it as the equal interval. If the distance between the points is not equal, then we called it as the unequal intervals. In a previous unit, we learn about the finite interpolation with equal intervals, that is Newton forward interpolation and Newton backward interpolation. In this session, we are going to learn about the Gauss forward and Gauss backward, which are the infinite for polynomials with equal intervals. So the first theorem is Gauss forward formula for equal intervals. In this statement, first of all, we have that y is equal to f of x is a function. Here we take the central values. For that, this y equal to f of x function takes the values both in the positive and the negative, including the y0, that is y minus 1, y minus 2, y0, y1, y2 and so on, and these values are obtained corresponding to the values of x, where x is the argument and y is the entry. Here x is equal to, comparatively, means for y minus 1 the value is x0 minus 2h. Here h is the equal interval between the points. So x0 minus 2h, x0 minus h, x0, x0 plus h, x0 plus 2h and so on. By giving these values, to prove the Gauss forward formula, we have to prove that yu is equal to y0 plus u delta y0 plus u minus 1 by 2 factorial delta square y minus 1 plus u plus 1 into u minus 1 by 3 factorial delta cube y minus 1 plus and so on, where this u is equal to x minus x0 by h. Here h is the equal interval between the points. Let's go into the proof. That first of all, we have to take that y is equal to f of x as a function, and which assumes the values from both the negative and the positive sides, that is y minus 1, y0, y1 and so on. By Newton-Gregory forward interpolation formula, already we have the forward formula, that is yu is equal to y0 plus u delta y0 plus u minus 1 by 2 factorial delta square y0 plus and so on, and the last term is u minus 1 and so on, u minus n minus 1 by n factorial delta power n y0. There in Newton-Gregory forward, the interpolation formula is finite, but in Gauss forward formula, the interpolation is infinite terms with equal intervals. Actually, we know that the forward formula for a y0 function, that is delta y0 is equal to y1 minus y0. When we do the delta square y0, we get the value of y2 minus 2 y1 plus y0. That means delta square y0 gets the value which is similar to the delta square y minus 1 plus delta cube y minus 1. Here we are using this concept to prove this formula. So from the delta square y0, we can write the delta cube y0 also. Similarly, we are writing here delta cube y0 as delta cube y minus 1 plus delta 4 y minus 1. Similarly, delta power 4 y0 is equal to delta power 4 y minus 1 plus delta power 5 y minus 1, and continuing. Similarly, from delta square y0, in place of y0, we are going to substitute y minus 1, and in place of delta square, if we substitute delta cube, then we get the similar formula, that is delta cube y minus 1 is equal to delta cube y minus 2 plus delta power 4 y minus 2. Continuing this one, similarly we get that delta power 4 y minus 1 equal to delta power 4 y minus 2 plus delta power 5 y minus 2, and delta power 5 y minus 1 is equal to delta power 5 y minus 2 plus delta power 6 y minus 2. Now substituting these values in the equation 1 to prove the Gauss forward interpolation formula for equal intervals. Now in the place of delta y naught, we are going to substitute delta square y minus 1 plus delta cube y minus 1. Then we get, then the equation 1 becomes yu is equal to y naught plus u delta y naught plus u minus 1 by 2 factorial. Here in place of delta square y naught, we substituted the previous value, that is delta square y minus 1 plus delta cube y minus 1. Similarly, in the next term, u minus 1, u minus 2 by 3 factorial, we get the value in a place of delta cube y naught, delta cube y minus 1 plus delta power 4 y minus 1 plus and so on. Now we are doing here simply solvation, that is we are separating the terms which are in the combined, that is yu is equal to y naught plus u delta y naught plus u minus 1 by 2 factorial delta square y minus 1, similarly plus u minus 1 by 2 factorial delta cube y minus 1 plus u minus 1 u minus 2 by 3 factorial delta cube y minus 1 plus u minus 1 u minus 2 by 3 factorial delta power 4 y minus 1 plus and so on. Now from the above step, we have that second and third term, and third and fourth term has the same coefficient, that is u minus 1 by 2 factorial delta cube y minus 1. We are taking it as a common in the next step. Then we get yu is equal to y naught plus u delta y naught plus u minus 1 by 2 factorial delta square y minus 1 plus u minus 1 by 2 factorial. Here from the fourth and fifth term, we are taking the common part, that is u minus 1 by 2 factorial. Then we get, in the coefficient of the first term is 1 and the coefficient of second term is u minus 1 by 3. By solving this value, that is by taking the 3 as an LCM, 3 plus u minus 2, then we get the value u plus 1. Continuing this in the next step, we get the formula, that is u plus 1 into u minus 1 by 3 factorial. When we did the same thing to the next term, but in a place of delta power 4 y minus 1, we are going to substitute the value of delta power 4 y minus 2 plus delta power 5 y minus 2. Then we get the next term. By solving this in a particular manner, then we get yu is equal to y naught plus u delta y naught plus u into u minus 1 by 2 factorial delta square y minus 1 plus u plus 1 u into u minus 1 by 3 factorial delta cube y minus 1. By corresponding these values, the next term is u plus 2. So u plus 1 u into u minus 1 u minus 2 by 4 factorial delta cube y minus delta power 4 y minus 2. By using the Newton-Gregory forward formula, we had proved the Gauss forward formula for equal intervals, and this was the forward formula. Similarly, we are going to prove the Gauss backward formula for equal intervals. In this, the process of doing the Gauss forward formula is similar to the Gauss backward, as Gauss forward and Gauss backward take only the central values. Here in this process also, we are going to use the same method which is used for the Gauss forward, that is Newton forward formula for equal intervals. Let's see the statement that if y is equal to f of x is a function which takes the values y minus 1, y minus 2, y minus 1, y naught, y1, y2 and so on, corresponding to the values of x. Corresponding to the y minus 1, we get the value x naught minus 2h. Corresponding to the value y minus 1, we have x naught minus h. Similarly, x naught plus h, x naught plus 2h and so on. Here h is the common, and that means equal interval between the points. Here f of x is equal to y. That means if y minus 2 is a function, then we get y minus 2 is equal to f of x minus 2h, and all these are the values obtained from the argument x, and the values of y from the function which we are getting is the entry. Then we have to prove the Gauss backward formula for equal intervals, that is yu is equal to y naught plus u delta y minus 1 plus u plus 1 by 2 factorial delta square y minus 1 plus u plus 1 u into u minus 1 by 3 factorial delta cube y minus 2. By taking this value, we can guess the next term, that is u plus 1 u into u minus 1 by 4 factorial, and the additional number that can be added, that is u plus 2. That means the next term should be u plus 2 u plus 1 u into u minus 1 by 4 factorial delta power 4 y minus 2. Here u is the x minus x naught by h. Let's enter into the proof, that is here also we are taking a function, that is y is equal to f of x. From that the corresponding values are y minus 1, y minus 2, y naught, y1, y2 and so on. To prove this theorem, here again we are using the Newton-Gregory forward interpolation formula for equal intervals. What is that? Yu is equal to y naught plus u delta y naught plus u minus 1 by 2 factorial delta square y naught plus and so on u minus 1 and so on u minus n minus 1 by n factorial delta power n y naught, and similarly that their u value is x minus x naught by h. In the previous theorem, that means in Gauss forward interpolation formula, we used that in a place of delta square y naught, we substituted the value of delta y minus 1 plus delta square y minus 1. But here we are starting from the delta y naught. As it is, delta y naught value means y1 minus y naught. When we do this, the value of delta y minus 1 plus delta square y minus 1 is also y1 minus y naught. That means delta y naught is equal to delta y minus 1 plus delta square y minus 1. Similarly, we can also write that delta square y naught equal to delta square y minus 1 plus delta cube y minus 1. Similarly, delta cube y naught is equal to delta cube y minus 1 plus delta power 4 y minus 1. Corresponding to that values, we can also write delta cube y minus 1 as delta cube y minus 2 plus delta power 4 y minus 2. Similarly, delta power 4 y minus 1 equal to delta 4 y minus 2 plus delta power 5 y minus 2. Delta power 5 y minus 1 equal to delta power 5 y minus 2 plus delta power 6 y minus 2. Now substituting all these values in the equation 1, that means we have to start from the delta y naught. In a previous theorem, we substituted from delta square y naught, but in the backward we have to substitute from the delta y naught. So let's see the next step, that is substituting in a place of delta y naught, delta y minus 1 plus delta square y minus 1, then the equation 1 becomes yu is equal to y naught plus u into delta y minus 1 plus delta square y minus 1 plus u into u minus 1 by 2 factorial. In a place of delta square y naught, here we substituted delta square y minus 1 plus delta cube y minus 1. In the next term, u into u minus 1 u minus 2 by 3 factorial. In a place of delta cube y naught, we substituted delta cube y minus 1 plus delta power 4 y minus 1 plus and so on. Then by solving this, that means taking the common terms apart, then we get yu is equal to u into delta y minus 1. Next term is u into delta square y minus 1 plus u minus 1 by 2 factorial delta square y minus 1 plus u minus 1 by 2 factorial delta cube y minus 1 plus u into u minus 1 u minus 2 by 3 factorial delta cube y minus 1 plus u into u minus 1 u minus 2 by 3 factorial delta power 4 y minus 1 plus and so on. By solving this, when we observe that the third and fourth term has the common part, that is u into delta square y minus 1. When we take this as a common part, we can solve the theorem as yu is equal to y naught plus u delta y minus 1. In next two terms, we have the common part, that is u and u by 1 factorial, that second term, and then we get that when we take the common of u, then we get 1 plus u minus 1 by 2 factorial. By solving this, we get the next term, that is u into u plus 1 by 2 factorial delta square y minus 1. In the next term also, we getting the common multiple of delta cube y minus 1. In a place of delta cube y minus 1, we are going to substitute delta cube y minus 2 plus delta power 4 y minus 2. By solving these two lines, then we get the next term, that is u plus 1 into u minus 1 by 3 factorial delta cube y minus 2 plus, and so on. By terms of the comparatively, the last term should be in a process like that. Yu is equal to y naught plus u delta y minus 1 plus u into u plus 1 by 2 factorial delta square y minus 1 plus u plus 1 u into u minus 1 by 3 factorial delta cube y minus 2 plus the next term should be with the positive side, that is u plus 2 u plus 1 u into u minus 1 by 4 factorial delta power 4 y minus 2 plus, and so on. In this process, by using the Newton-Gregory forward formula, we can solve the two theorems, that is Gauss forward interpolation formula and Gauss backward